So I think my talk will not actually be about factorization algebras. I think I just gave this kind of generic title. You know. Well, I'm glad I did, because I think listening to what people's questions today made me really think about what would be good to talk about. Now, I was also a bit worried about coming to a workshop about the 2-0 theory, because if you want to learn something about quantum field theory, this is absolutely not where you should start. 2-0 is the hardest quantum field theory. So, but on the other hand, it's been great that most of what we've been learning so far has been about more understandable things in lower dimensions. So what I want to talk a little bit about today is firstly some generalities on how people might think about field theory from a homological point of view, and secondly, how to understand various twists of supersymmetric gauge theories in various dimensions. So I'll give it, we saw from Tudor and from Andy some description of, supersymmetric field theories. There's a bunch of fields and some action and so on. And I always found it a bit confusing. But there's something nice that you can take the cohomology, you can extract some simple piece, which you can write down in a much simpler way. At least much more natural to mathematicians, I think. Okay. So what's the basic idea of what a field theory is? Well, everybody knows the kind of Lagrangian picture. But a more homological point of view is of dimension n. Strategy to make it invisible. Yes. Well, I don't want to be on the record somehow, so I don't think this will be picked up by that. So field theory of dimension n sends M, some compact manifold, to something very fancy, a kind of derived stocky thing. But I think, I somehow came to this workshop thinking, you guys will all know this derived stack stuff. I just have to explain field theory. But I'm suspecting that's not the place to start. But I'll say a little bit about this in a second with the symplectic form. Of degree 1. Plus 1. Sorry, minus 1. Poisson tensors of degree. So there's been a lot. This is called the BV, Batlin-Vilkovisky way of thinking about field theory, and there's been a lot of work on this. I learned about this from some beautiful papers of Albert Schwartz in the very early 90s, Kontsevich. And kind of a better perspective on the global theory was being developed by Pantev, Toen, Vacchier, and Vizzozzi more recently. So the nice thing about this picture is there's kind of a simple universal way to construct very many field theories. But anyway, what's a derived stack? So whatever a derived stack is, well, we don't really need to know what it is in kind of full detail. But an important point is if I take some point in it, then the tangent space is a cochain complex. So the symplectic pairing will give an isomorphism from the tangent space of x to the cotangent space with some shift by 1. So what's nice about this is that these derived stacky things arise often in nature. So example, here's how you would describe Chern-Simons in this language. Suppose that M is a 3 manifold. We consider the space of flat G bundles on M. Well, the derived space, if I take the tangent space this moduli space of flat G bundles, this derived moduli space, well, we know it's quasi-isomorphic to the RAM complex of M, with coefficients in the adjoint bundle, shift of 1. So we know if we've ever studied deformation theory, how do we deform a flat G bundle? We can add a 1 form to the connection. That'll be something in omega 1. But then I divide by gauge, so omega 0 is some kind of quotient. And this 1 form must be flat, so its image in omega 2 is 0. So that, for example, the cohomology of this complex, so H0 of this complex is H1 of M, coefficients in GP, which is what you would normally think of as a tangent space to this classical moduli of flat G bundles. Now note that Poincare duality gives an isomorphism from, say, H I of M GP isomorphic to H 3 minus I M GP, so that this is our symplectic pairing. And if you think about how the degrees work, it really is of degree -1, because it pairs a 1 form, which is in degree 0, with a 2 form, which is in degree 1. Now, OK, you have to check. I've written down this 2 form. I haven't checked that it's closed. It really gives a global 2 form. But this is actually not hard. Essentially amounts to this being an invariant pairing on this Lie algebra. But that's nice. So, well, without ever writing down a formula, I've described Chern-Simons. I hope this is a plus, maybe not a negative.
So what does it mean? Like, how does that? What does it mean you describe Chern-Simons? A lot of Chern-Simons involves like flat fields, not just flat ones.
Well, this is classical Chern-Simons. This is the space of solutions of the equations of motion of classical Chern-Simons. But you can, because it's symplectic, this space of solutions is some kind of DG manifold. Because it's symplectic, this differential, which is a vector field, is Hamiltonian. That Hamiltonian function is the action function. So from this procedure, we can recover the action function. What I should have said, you might worry about, well, things up to quasi-isomorphism and so on. But to get a kind of stronger picture, and better, this is going to be a sheaf on M. We have a sheaf on M, which sends U to, in general, it will be the solutions of the equations of motion of U. The sheaf of derived stacks with the Poisson structure on Evie open. U, which is kind of compatible with these maps. And being pedantic in that it's not, strictly speaking, a sheaf of Poisson manifolds, because the limits in the category of Poisson manifolds are not the same as they are in ordinary manifolds. Well, and also, I want to make, for a compact manifold, we wanted it to be symplectic. But on an open set, I said it was Poisson. Well, but this Poisson structure is not just any Poisson structure. It has its own non-degeneracy condition. It's just a little bit weaker. So let me explain that. So non-degeneracy. So if I take some, say, F, which is an solution to the equations of motion on U, then the pullback of this tangent bundle is a sheaf on U of complexes. So the Poisson structure will relate the dual of this to this guy. What we wanted to do want to have an isomorphism from dual an isomorphism from this sheaf to its dual, but now you might ask, the dual of a sheaf is not a sheaf, so what do we really mean by dual? What goes on here? This is the Verdier dual. So let's check that this happens in Chern-Simons too.
So you're writing F upper star just means the fiber at L.
Well, yes. So I think I'm abusing notation. So this is just going to, the fiber of F will be a vector space, which will be the vector space of sections of this sheaf on U. But F is a section, so it gives a section on any open subset. So in particular, for any open subset, I have a vector space there as well, namely the tangent fiber to equations of motion on V at that. So in this way, I really get a sheaf on U. I'm using the fact that the tangent model is functorial. So what happens with Chern-Simons? If I take just some kind of U inside of M, then again, the equations of motion on U is something like local systems. Then I take the tangent space U. This is going to be the Ram complex GP, the shift of 1. And by, what's the, I don't recall the name people use for Poincare duality on something non-compact. But anyway, this is there a special name? I don't. It's the dual of the compactly supported homology. Could be isomorphic to the compactly supported homology GP dual. And this is the sections of the Verdier dual. So it really has this kind of feature we want. OK. So for the purposes of this talk, the reason I'm introducing this concept and this notation is that I never want to write down an action functional. I want to give you some manifold and say, this manifold is just kind of, and say, because of the geometric structures in this manifold, I get a field theory, classical field theory.
So the entire discussion is about classical.
So far. I mean, this, I don't think I'll tell you much about the general procedure for quantizing these kinds of things, but I will tell you in examples how it works.
Just so I understood, so the definition that we have now of field theory is something which associates to every manifold some derived stamp which shifted symplectic structure.
Yes, exactly.
And maybe the sheaf of Poisson's.
Yeah, but that's, yes. The sheaf of Poisson stuff is important to get kind of local information. OK. Where was I going? So one can ask, what structure on M, M was my manifold, what did I need in order to be able to have this symplectic structure? Well, as you can see, all I needed was some kind of Poincare duality, which is some way to integrate functions, integrate differential forms. But if instead of taking flat bundles in M, I took holomorphic bundles, you might expect there to be something similar as long as I was in a situation I could integrate holomorphic functions when I had Serre duality. So this is another example. holomorphic Schoen-Simons. Schoen-Simons, if I take x and Calabi-Yau threefold, then I take Lun-G of x as a shifted symplectic pairing. And it satisfies these kind of features too, that it works locally as well. And why is this? The tangent space on G of x is that the Dolbeau complex of x with coefficients in the adjoint bundle, the shape of 1, and using Serre duality, even if x is not compact, this is equivalent to the dual of the space of compactly supported, the compactly supported Dolbeau complex by Serre duality. You know, I learned recently that Serre's original paper was about the non-compact case. I mean, with this infinite-dimensional functional analysis case, which I had never learned of until recently. But, so this implies the desired pairing. Symplectic pairing at the level of tangent spaces.
I should not be concerned about the infinite dimensionality of these things.
You should be concerned, but I would like to reassure you that one can deal with these. You know, this is a quasi-isomorphism of cochain complexes of topological. It's a homotopy equivalence. Cochain complexes of topological vector spaces. So Serre's original paper was all about this issue. And now you see, you know, the topological field theories are typically the ones where these spaces are finite dimensional. Here, this is not a topological field theory. Okay. Let me give you, let's see how we go. And of course, you can take kind of mixtures of this. Okay, kind of if we're on, say, C2 cross OR, we can look at bundles. Bundles which are holomorphic on C2, and kind of flat on OR. On OR, we also have the structure. We also have the structure for the same reason. We have this structure. Okay, so now I hope people have some feeling that there's, you know, some kind of bunch of field theories that we can write down, which are, you know, some directions are topological, some are holomorphic, and there's some volume forms. We can do this.
If I put S1 instead of O, do I get this like Microsoft nonsense?
Well, this is not related. This is related to a field theory with less supersymmetry. I think n equals 1 in 5 dimensions, I think. But yeah, I think the Nekrasov nonsense was you have some kind of interesting C2 fibration over the circle. Where around the circle you have monodromy, and you do this kind of thing.
Can you elaborate on what shifted Poisson structure is?
Okay. So shifted Poisson structure and the simplest thing to say is at the level of functions, if I have x as some kind of derived gadget thing, then functions on x will be a differential graded algebra. And, you know, as some kind of baby approximation to what this derived world is, you might say derived things are, you know, they look locally like they look locally like spectra of differential graded algebras. I mean, it's not really true, but that's how people thought of this stuff in the early 90s before they learned better. Then the Poisson structure, I take two functions. It's just what you think it is. Take two functions. I will get a new function, the Poisson bracket, which is of degree, the degree of degree f plus the degree of g plus 1, and which satisfies usual axioms, Jacobi and Leibniz rules. Now, if you're a fancy person, you can ask for things to hold up to homotopy and so on, but that's not really important for this talk. So let's give you more examples. So this next example is going to be Rosansky-Witten theory. Suppose that X is an ordinary, for example, a holomorphic symplectic manifold. M is a 3 manifold. We can consider the space maps kind of from M to RAM. I'll use this notation. This is the space of locally constant maps. To X, and the tangent space at some particular map to this mapping space is
constant map to X.
it's well, yeah. It's what's happening is this field theory, the equations in motion of this field theory, tell you that the maps are constant. This does not imply it's a trivial field theory. There's interesting stuff. And there's interesting, like, nilpotent stuff. What's wrong? Look, suppose X is a vector space.
Okay.
There's a sheaf of locally constant sections. We can take this sheaf cohomology. This is what's going on. So we get some drive space by locally the constant maps. We're taking the nonlinear version of sheaf cohomology. So in particular, the tangent space is really just going to look like the sheaf cohomology. Differential forms on M with coefficients in the pullback of tangent model of X. Now,
could M Durand be a thing which is not just notation? Is there like some stack could put there and then have that be a definition?
If I took some complex manifold and then I could take it to the RAM stack, that would be totally fine.
Okay.
Yeah, and I think in this world, what you should do is, any topological space can be made a drive scheme by a drive stack. Think of it as constant special set.
Constant special stack.
And that's this. But I prefer to use differential forms personally, because that makes the connection with physics clearer. These differential forms really will be like various fields of my theory.
Sorry, could I suggest that you don't write so low?
Oh, I'm sorry, I'd forgotten that.
Yeah.
Sorry about that. Let me write this one again. So the tangent space to F to this mapping space is RAM complex of M spare T and T of X. And now we're supposing X is a symplectic form. If X is symplectic, then if I take two tangent vectors, alpha, beta, star T of X, then I can define a new symplectic form, say omega M alpha beta, to be the integral over M of the symplectic form X. Okay, I just apply the symplectic form here to get differential forms in M, then I wedge them and integrate. Now, this is a form is a symplectic form of degree -3. Okay. Now, -3 is not the same as -1. And we said we wanted -1 to construct a field theory. So what do? Well, we know Rosansky-Witten theory is a Z mod 2 graded field theory anyway. So that's OK. So if you take h bar to be a parameter of degree -2, then this symplectic form is a -1 symplectic pairing on this mapping space maps from m gram to x, so giving us a field theory.
This h bar is behaving kind of as a purely classical parameter. If I were trying to write down a quantum thing, would I have a second parameter controlling the size of quantum corrections?
No, this will be the parameter controlling the size of quantum corrections, because if you think about quantum mechanics, it appears as 1 over h bar in the action functional. And the action functional, if I think of the action functional as the Hamiltonian vector field for the differential, it scales.
I mean, because normally I get the Poisson bracket back as something like 1 on h bar times the commutator bracket.
Right. So if I invert this, I get h bar times the Poisson bracket, because the Poisson bracket is the inverse of omega. So that's like the leading quantum correction will be this.
Right, so where did h bar come from?
I introduced it to formally make this into, well, there's two ways to say. I could say, I work in the Z mod 2 graded world, so therefore I don't care about the difference between -3 and -1.
Okay.
That's totally fine. Or you could say, well, I'm always going to be, when I quantize, I'm going to be doing perturbation theory anyway. You often are. And you can make it into a Z-graded theory by giving this parameter you quantize with some degree. That's all. So it's a purely formal game. This is not an important step.
So whenever we have a shifted symplectic structure or shifted Poisson structure of any degree, can we make it into a -1?
Any odd degree.
Why does it matter that h bar is even degree?
Well, because you somehow want to evaluate h bar equals 1. I mean, you wanted to.
1 doesn't have degree matrix.
What's that?
1 doesn't have degrees.
Violate Costello rule of signs.
Like, oh.
But like,
That's right. That's the answer to his question? Yes, that's the right answer. Yes.
But like, is there Donaldson-Thomas theory on 5 manifolds? Like, usually I thought you perform it from this mapping stack construction, and the reason it works on 3 manifolds is because we're mapping to BG, which is 2 shifts.
Yes.
Oh, so the answer is yes. It does
Yeah.
exist on 5 manifolds.
But is there, sorry, is there what exists in 5
Does
manifolds?
Donaldson-Thomas theory exist on 5 manifolds?
Donaldson-Thomas theory.
Like, you form the mapping stack, and you get something -3 shifted.
But I mean,
You get this formal trick.
yeah, I mean, no, I don't. Yeah, that's not going to work. I mean, as Nick said, cultural rule of science is.
I don't know. Some people get great.
Yeah.
That's why I asked for 5.
Well, here, that's not the problem. The problem probably is going to be that the other characteristics are not going to be fine because you did this. It doesn't make sense because you made things too periodic. The way you get Thomas invariance is a Euler characteristic or something. I don't.
Yeah.
Euler characteristic of two periodic
Yeah,
things
okay.
is a trickier notion.
I don't know, take the even one, like, in one component minus the odd one. Sounds pretty reasonable to me.
No, he's saying, like, if you add them all up. No.
But why would you do that?
Well,
He wants to.
Great. So now we understand Rosansky-Witten theory. So the first thing, I think everybody understands Rosansky-Witten theory. Can I get it?
So why was it important that this thing was holomorphic symplectic?
We use some kind of symplectic form to get this omega. Oh, yes, and why could it not be real symplectic?
Yeah, why not?
Oh, that's totally fine. I think the reason physicists would say you want it to be holomorphic symplectic is that this arises as a twist of an n equals 4 supersymmetric gauge theory. And for the n equals 4 supersymmetry, you want a hyperkähler metric. And we're okay, so yeah.
Well, even in a sigma model, you want the hyperkähler metric on the target.
Yeah, but this is yeah, I agree. Yeah, even this in the n equals 4 sigma model. But this is, of course, this is something weaker than the sigma model, which happens to be defined. It's independent of the metric.
understand something simpler. What happened if, since we decided all odd numbers are the same, what happens if M is a 1 manifold instead of a 3 manifold?
Oh, then you get quantum mechanics.
Okay.
Topological quantum mechanics with zero Hamiltonian. I think as Tudor will explain, I think at some stage, but I think this is part of your story that, if I took a 3 manifold and I did this Nekrasov nonsense and I went equivariantly in the normal directions, then I would just get literally quantum mechanics on this manifold. So, is there another black pen? Or, oh, yes. Okay, so this generalizes. Suppose instead of some holomorphic symplectic manifold, I took some kind of holomorphic symplectic stack. Suppose if, say, as V is, let's do the situation Tudor and Andy were explaining. Suppose that V is a symplectic vector space. Space over C, complex symplectic vector space. G is a group. And then G acts on V, preserving the symmetrical form. Omega. Then we can construct the symplectic reduction. Then I can form, well, in this story, nothing told me this had to be an ordinary manifold as opposed to a derived stack. So, which I view as a stack. This is important. Derived stack. Derived means we don't just impose the moment map equations. We take care of the non-transversality in these moment map equations by replacing it by a causal complex. And we also remember stabilizers.
Am I allowed V to be the 0 vector space?
Yes, that will be the pure gauge case. So if V equals 0, what you will find is the cotangent bundle of BG. So the cotangent fibers arise from the moment map equations.
Should I be taking G a real group? Or
No, here G is a complex group, complex algebraic group. But it's going to be the complexification of the group that Tudor talks about. Then Rosansky-Witten theory, and then we can define Rosansky-Witten theory on this quotient. And it turns out, as I will say in a minute, this is one of two topological twists of n equals 4 gauge theory.
When you say T star BG, that's really the cotangent bundle, not the odd cotangent bundle?
No, it's really the cotangent bundle, because you want to get something ordinary symplectic.
Oh, that's, yeah.
But because the tangent bundle of BG is in degree -1, the cotangent bundle will be in degree 1. And okay. So how am I doing for time? Does any?
You have till 4:30 by the schedule, but of course.
Well, isn't Andre speaking at some stage? Andre Enriquez?
No, not today.
Okay. What's the time though? Oh.
You have 20 minutes.
Okay. Okay. I wanted to get
Is
to.
there someplace I can actually learn how to construct V mod mod G as a derived stack? Why would I?
Well, I can tell you. But I mean, if you know how to take the derived version of solutions of equations and the derived quotient, then you know how to do it.
Okay.
And you should know how to do both of those things because they're.
Okay.
I mean, yeah. The derived solutions of equation is just like the complex, right? The causal complex. So maybe that's an important point. What's the tangent space at the origin of V mod mod?
I should just interrupt to say that there will be a discussion section tomorrow.
Okay.
Ah, yes. I mean, as an example, what does this look like? The tangent space looks like V in degree 0, G star in degree 1, G in degree -1. What's the point? You know, the moment map equations are quadratic, so they don't change linear deformations. This will impose the moment map equations, and this is the gauge symmetry. Okay.
And it looks like that with some differential, right?
It has some Lie bracket, but no differential, because if there's a linear action, it preserves. Yeah. Now, this acts on this, and then there's some Lie bracket if you want, which is the moment map. There. But yeah. Once you shift it, then sorry, there's a Lie bracket. Where are we going? So I want to say briefly what twisting is. And then explain. I mean, my aim today was, firstly, I wanted to introduce this class of field theories. The reason this class of field theories is really good is that, as far as I can tell, every supersymmetric theory in dimensions less than 6 can be written in this way. I mean, these are all the ones I know, all the ones we've been talking about. They have some simple description in this way. And you might disagree that this is a simple description,
But like that whole chart you can do.
Pardon?
The whole chart that's over there, you can.
Except for theory X. I think so. I mean, yeah. This Kovanov-Witten one is tricky too, but obviously that's really hard. But most of the ones, I think all the ones which are Lagrangian theories have nice descriptions.
And does the way you play this game have something to do with this? I mean, each of those things has a manifold written next to it. Does it have to do with that manifold?
Yes, you're going to do some. I mean, you know, one example, we reduce to 3 dimensions on a surface across a circle. We get Rosansky-Witten theory with the target Hitchin system. So it's going to be that kind of thing, I think. Although, yeah, again, the class S theories are mysterious too, because they also don't have a Lagrangian description, so that's going to be tricky. So what's twisting? So we take what is n equals 4 supersymmetry in 3 dimensions. As Tudor explained, kind of there's some extension of the Poincare algebra by an 8-dimensional odd vector space, which looks like S tensor C4. What's S? S is equal to the fundamental representation of SL2, which is the same as SO3. Sorry, spin 3. You know, there's a unique spin representation of spin 3. So 4 copies of this gives you the n equals 4 supersymmetry algebra. 4 dimensions of the fermionic part. So if I choose some Q tensor C4 such that Q brackets Q, where does Q brackets Q live? This is some translation. Is 0, then what can we do? We can take, so supersymmetry, this algebra acts on everything, our Hilbert space, our spaces of operators, whatever we can think of. I've chosen an element of it a square 0. That means I can take cohomology of everything. The twist is obtained by taking Q cohomology of everything. Okay? Well, maybe a slightly better way to say it is that, of everything in our original field theory. So, or better, the original theory has some kind of beta RST differential. say, acting on the Hilbert space and everything else.
Wait, just so I understand, at the beginning you told us one definition of what a field theory was supposed to be. This is now when you say theory, you mean the usual notion of theory.
Well, the usual notion of theory gives you one in the sense I said by taking the derived critical locus.
Okay.
So I mean, every Lagrangian theory is a theory of this type. Non-Lagrangian theories, nobody knows anything about them. So
I mean, the derived critical locus, I mean, how to say it? A priori, it's on like infinite dimensional thing and infinite dimensional space, right?
yes, but on a compact manifold, your field equations are always elliptic modulo gauge. So on a compact manifold, it's always a finite dimensional space.
Ah, thanks.
But locally, maybe infinite dimensional. So the original theory has our BRST operator, which is how you construct, how you describe gauge theories. And what we're doing is we're replacing, we send this guy to plus Q. So you can think about it as some kind of deformation of the theory. Now, I don't want to go into details of this. But the beautiful thing is that this makes everything much simpler. So what I want to do is, time okay, or?
Sure. Well, you have 10 minutes by the clock, but feel free to.
So what I'm going to do is give a description of the twist of the n equals 4 guy. So if I choose my Q, which lives in, say, S, one copy of S. I have 4 copies of S. It lives in 1. What am I saying? That will not square to 0. Choose Q of the form, say, Q1, I, Q1, 0, 0. This is kind of orthonormal basis. C4, sorry. Well, then Q squared equals 0. And you find that the image of Q inside of complexified translations is 2 dimensions. So, of course, C3 is just our complexified. I'm sorry, I feel I'm not being very clear right now. What I'm trying to do is describe what the twist of this n equals 4 theory looks like. So I first have to tell you what kind of supercharge I'm using. I'm not using a generic one. I'm using the least generic one, which squares to 0. So I can take its image. The image is going to be 2-dimensional. So it contains something like d by dx1, then d by dx2, it's I d by dx3. Now, things in the image become trivial. Sorry, I'm writing too low. Operators which live in the image of Q are trivial in the twisted theory. So implies, well, suppose the image of Q contained everything. If the image of Q contains everything, then this theory is topological because it has no Hamiltonian in particular. And the momentums, the quantization of these translation operators in the Hilbert space are, energy and momentum. They're all 0 in topological theory. In the topological twist, precisely because they're in the image of Q. But here it's not quite topological. It's topological in the x1 direction. Maybe I'll make this a minus sign. And holomorphic in the x2, x3 plane. So what is this? It's just a slight variant of this Rosansky-Witten theory we were discussing. Say on so let's see, so 1 second. The moduli of equations of motion on sigma cross S1 are maps from, what do we do? Here instead, so let me remind you briefly of something. So we discussed how if I had a 3-manifold and some holomorphic symplectic manifold, I can make this Rosansky-Witten theory. But all we needed was some kind of volume form. So here what I've done is replaced sigma de Rham across the circle by the shifted cotangent bundle of sigma de Rham. So the point is, shifted tangent. The point is that functions on, say, T of 1 sigma across the circle are, so the Dolbeault complex of sigma, omega star star sigma, tensor, the de Rham complex of the circle, with differential, which is like a d bar sigma plus the de Rham differential on the circle. Okay, so we've done exactly what we've done before, except instead of using the de Rham differential on sigma, we've used just the Dolbeault differential. So kind of Serre-duality implies that we have a field theory. And the claim is that this field theory is this twist. The twist, the non-topological twist. So for example, if I work in flat space on C cross OR, and if I just choose my group G to be trivial, we find free theory where the tangent complex, which you can think of as some version of fields, linearized fields, is the Dolbeault complex of C tensor the de Rham complex of OR, join some epsilon, or epsilon tensor V is of degree 1. So this is exactly what you would get if you twist this free hypermultiplet. I mean, somehow you should interpret it as, we expand this. I mean, the 0, 0 parts, that's a scalar. The 0, 1 parts and the form parts, they're very spinors. So there's a bunch of scalars and a bunch of spinors. There's kind of 2 copies of everything. Yeah?
So one way to describe twists is to describe a non-trivial map from the Poincare group into the R-symmetry group across the Poincare group.
Yes.
So is there a description of this twist in those terms?
There is. I might have trouble remembering what it is. So what we're saying is that if if you read Witten's papers on twists, he doesn't emphasize his Q-cohomology point. He emphasizes a different point, is that when you want to put it on some compact manifold, maybe you want to treat your spinors as being, sections of being differential forms or something like that, which means you change the action of the spin group. But really, the best way to think about it is you really should do both. Firstly, you should change the action of the spin group, and then you should take Q-cohomology. This particular twist is not a topological twist, so will not be described in that language completely. But the topological twist we'll see later will be in certain circumstances. It's kind of tricky, I think. I'm mostly interested in flat space. Okay, do I have one more minute?
Sure.
Please, you can tell me actually what the time is. I don't know.
Oh, no, you still have the process as you have a minute.
Okay. Okay, so I hope everybody, understands this n equals 4 theory now. Please. But what I haven't explained is we've taken this kind of holomorphic twist, but there's also further topological twists. And it turns out there are two of them. Now, there are two further topological twists. Well, these original supercharges I had, some of them, the ones which commute with the supercharge I chose to twist by, will descend to this twisted theory. These come from here. Here they come from very simple vector fields. D by d epsilon and epsilon d by dz. These are odd symmetries of my space of fields. These odd symmetries, clearly they commute to translation in Z, which is what we want from a supersymmetry algebra. So this epsilon d by dz twist, what does it do? It simply turns back on the Dolbeault differential. So it turns on the de Rham differential. Sorry. On sigma. On C. So this gives us Rosansky-Witten theory. Call this the B twist. So on d by dz is the B twist. The reason for this terminology is when we reduce to 2 dimensions, it is the B twist. On the other hand, the d by d epsilon is the A twist. Well, just like the A model in 2 dimensions, this turns this into a field theory, which in perturbation theory has nothing interesting going on. But this mixes a field theory where we count solutions of the equations of motion. And the equations of motion, say on C cross R, which are essentially maps from C cross R into my quotient, which are holomorphic in C and constant in R. Now, the final statement I want to make is that just like in the A model, so just like in 2-dimensional mirror symmetry, where the A and B models aren't interchanged, exactly the same thing happens here. So 3D mirror symmetry interchanges the A and B twists. So the A twist is going to be related to the Coulomb branch. The B twist is going to be related to the Higgs branch. OK, so I think,
What do you do to V and G to get the mirror symmetry?
well, I don't know of an algorithm. I know of examples. But Tutor knows much more than me about this.
It's not something like you just trade G for G check and V for something stupid.
No. Well, you can ask, well, I'm going to talk about this next time, but the pure gauge case when V is 0. What happens with the pure gauge case is to interchange for, I would shade the group by its dual, and then I take the symplectic reduction of the cotangent bundle of the dual group.
There is no general, and there are cases where there is no gauge theory here, so there's no G dual and G dual.
Okay, so next time I want to say, I want to move on to higher dimensions, but I also want to say a little bit about how to do some computations in the A-twist. I know this is also what Tutor is doing, and he knows much more about it than I do, but maybe this perspective might, together we might understand something. Yeah, stop there.